So, today we're going to talk about binary numbers. Yay! Computers, they usually work with the binary number system. So we as people, we are used to the decimal number system, where we have 10 different symbols that we can use to express numbers. Yeah. What are those 10 different symbols? Now, if you think of any number, think of a number. 8, yeah, okay. So 8 is one of those symbols, yeah? 9 is another number. So the 10 symbols, what are the 10 symbols we use to make up numbers?
0 to 9.
1 to 9 and? 0 to 9, 0 to 9, yeah, very good, 0 to 9. 1 to 9 is obvious, and the 10th symbol is the 0. And as it happens very often, there are those people who think of theoretical ideas, theories, and they come up with those theories, and actually much later those theories became very important. Yeah? I mean, the people who came up with Google, they were interested in a specific mathematical way of basically linking elements together. Yeah, I'm simplifying here. And then the idea was suddenly, actually, this can be used to create a search engine to figure out basically, which websites are important for certain keywords. Yeah, you search for, I don't know, umbrellas, yeah, and Google will come up with a website that's suitable for umbrellas, and so on. So obviously, very good, very useful. There were lots of other different search engines, but in the West, Google is basically the search engine everybody goes to. Yeah. So we have Gottfried Wilhelm Leibniz, 17th century, and he came up with this idea of binary numbers. And he was a xenophile. And as part of that, he came across the I Ching. Anybody can tell? Have you heard of the I Ching? Say no. No. So, can you, since 95% of the students here are from mainland China, can you tell your classmates what the I Ching is? I Ching. Yeah, I did the tone wrong, didn't I? I Ching. What's the I Ching? What is it? Can you explain it to your classmates? Have you heard of the I Ching? Have you heard of it before?
Yeah.
Yeah, what is it? Philosophy. Are you satisfied with that explanation? Your classmate would like to know more. Okay, who has not heard of the I Ching? Okay, so which means you all heard of it. What's the I Ching?
I don't know how to explain it.
Have you seen those symbols before? About the future. Okay, how does it work about the future? How does it work?
I don't know.
Okay. Well, I think your classmates are gonna wiki it soon. If there's no anyone? You all heard about it. You all have enough idea what it is. Can you try to explain it to your classmates here in the first row? Are you looking for an explanation? Try to explain it in your own words. Gonna work. You're all wikiing it yourself, aren't you?
What?
Okay.
A book.
It's a book, okay.
Talking about the philosophy.
Yeah, very good. And there are different symbols in there as part of the I Ching. So actually, Leibniz, so he was a polymath. Have you seen those before? No? I like to eat them. They're named after him, but unrelated story. Okay. So he saw this and he actually realized that the I Ching, there's some sort of system going on here. Yeah? This would be one of the symbols of I Ching. This would be one of the symbols of I Ching. And what we have here is actually the binary number system, which is the number system used by any computer. Yeah? Internally, now the computer might show you a decimal number, the kind of number we are used to, but internally in a computer, the numbers would be stored binary. Yeah? If you think a computer has copper wires inside, so with a copper wire, there's either electricity on it or there's no electricity on it. Or a computer wants to store information on a hard disk. Yeah, a hard disk is basically just a magnetic disk. You either make it magnetic or you don't make it magnetic. Yeah? I'm obviously simplifying here. Or the same music CD or data CD. Again, I'm simplifying here, it's a bit more complicated, but either there's basically a little hole in the disk or there isn't, and it will either reflect the laser light or not. So basically, in an IT system, things are communicated, things are stored binary. And the binary system works exactly like the decimal system that we are used to. But because we are not used to thinking about the rules of the decimal system, because it's so in our brain, it's quite difficult for us to understand the binary system. But exactly the same rules apply as with the decimal system. Why do I talk about it? Because I also want to talk about the hexadecimal number system. And that is what we will use for colors on the web, on any web page. Okay. So the problem here is we are all used to the decimal number system. There's a famous guy here, Daniel Kahneman, and his idea is that there are two systems of thinking in your brain. There's system one, which is fast, which is emotional, which is stuff we are trained to do. So I'm going to ask you a question, I'm going to pick you. 2 plus 2 is? 4. Yeah, you knew it immediately, yeah? You were using the system 1 in your brain. Yeah, very easy. I ask you another question. Let's say 13 times 7. Now you have to think. Yeah? That is system 2 in our brain. So the problem here is decimal number system, we are so used to it, it will be system 1. We can do it without thinking about it. If any of you have a driving license, maybe you know that you drive around and suddenly you realize, did I already drive through the town? Because you actually, your brain did it for you. This is system 1. System 2, we think about it. So the problem here is not that the binary system is difficult, the problem is that we need to use system 2 to understand the binary system. Okay, let's have a look and let's explain the rules of the decimal number system first. And I'll have to change my screen here. If I touch the cable wrong, it will crash usually. Oh great, now I don't have an escape key. Let's plug that in again. No. Yeah. Come on. Here we are. So. Come on. Oh, it didn't work, did it? Where's project? Okay, and here we are. Okay, so tell me again the symbols we have in the decimal number system.
0, 39. 4, 2.
Okay. So, how does it work? What's if I want to show the lowest value possible? What value is that?
0.
0. Okay. And I want to show the next higher value. What value is that? 1. Okay. So how does it work? If I want to go to the next higher value, I just basically move up 1. What's the next higher value after 1? 2. What's the next higher value after 2? And you? What's the next one? 4? Okay. Great. Okay, we do that all the time, and in the end we hit 9. 9 is gonna be difficult. What do we do when we hit 9? We don't have more symbols at our disposal. So if we want to go to the next higher value after 9, what do we do? What's the next number after 9?
10.
Okay, so how did we get there? We basically reset our number. So we could say, we could think of it as 9, or we could think of it as 09. Doesn't really matter. Works either way. So we reset the last digit to the first value. Yeah. And we then increase the next digit. Yeah, it used to be 0, and now we make it. What's after 0? 1. Okay. Yeah. Okay. What's the next number after 10? 11. Yeah. So how does it work? We just increase the last digit. Okay, we do that, and then in the end we hit 19. So what do? We reset the 9 to we reset the 9 to 0, and we increase the next digit from 1 to 2. Yeah. Okay. Yeah. So I think we got it now. And we do that until we reach 99. Let's do that example. What happens at 99? We want the next higher value. What do we do? Yeah, we reset the 9 to 0. Yeah. And which means we need to increase the next digit, which is 9. We reset as well because we are at the highest point. Yeah. And then 1. Yeah. Okay, we are all clear how this works. Yeah? But normally we don't think about how it works because it's a system 1 thinking. Binary numbers work exactly the same way, but we only have 2 possible symbols. Can I do it a bit thicker? Okay. We only have 2 possible symbols. That's 0 and 1. So what's the lowest possible value? 0. Okay. So after 0, what's the next value? 1. Okay, what's the next number after 1? Exactly the same rules apply. No, there is no 2. There is no 2. Apply the same rules. You have to switch from system 1 thinking to system 2 thinking. You apply exactly the same rules. What happens? We reached the end. So what do we do with the 1? The 1 gets reset to 0. And then what do we increase? We increase the next digit. 1. Yeah. Okay. What's the next number after 1, 0? 1, very good. Or are you just consulting the I Ching on this? Also a valid option, because it's in the I Ching. I Ching, I should say. I did the tone wrong again. What's after 1? So we need to, let's do it logically. We need to increase the last digit, which is a 1. We can't increase it because we run out of symbols. So the 1 becomes a... Yes, say it loud. 0, yay. And now we increase the next digit. The 1 becomes a 0. Yeah. Now we increase the next digit. 1. Yeah, very good. Let's do it a bit longer. Huh? Yeah, very good. Look, it's starting to become slowly, if you do it a bit more, it could become system 1 thinking. What's the next one? Yeah, very good. And? Yeah, and now? Difficult. Next one. Yeah, okay, very good, very good. And now I'm gonna write down the decimal equivalent above. Yeah, so this is a decimal 0, this is a decimal 1, this is a decimal 2, this is a decimal 3, 4, 5, 6, 7, 8. Yeah. So this is the reason why there are certain numbers you will come across. Yeah, if you buy your iPhone, if you buy your Android phone, who has a how much memory does your iPad have? Do you know?
This one, I'm not sure. So this one got 512 gigabytes.
512, yeah. So that's one of those typical numbers. So 512.
101.
For 512, we basically need 9 different digits. So basically, if you have a binary number of 9 digits, yeah, you have all possible combinations between 9, 1, 2, 6, 7, 8, 9. Yeah. If you have 9 digits, you can have 9 zeros. Yeah. The next one is 1, yeah, and that goes all the way up to 1, 1, 1, 1, 1, 1, yeah, and so on. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yeah. So that would come up with, if we have 9 digits, we have 512 possible combinations we can basically represent. If we have one more, if we have 10 digits, we have 1024. 1024 is 1 kilo. If we have 1024 kilos, we have 1 mega. If we have 1024 mega, we have a giga. So you said you have 512 gigabyte. Yeah. So that basically means, yeah, kilo is 10 bits. Mega is another 10. Giga is another 10 plus 9 to make it 512. So you probably have something built into your device that can store 39 zeros or ones. Yeah. And that can come up with basically 512 giga. And that would be gigabit. And then times 8. Even more. Because this is bit, not byte. Okay. But this is where all these numbers come from, yeah? Let's say we have 2 possible combinations, 2 bits, yeah? Two bits, we have 4 possible combinations. If I add 1 bit, we have the same. Yeah, we have 8 possible combinations. I add another bit, we have 16 possible combinations. Another bit, 32, 64, 128, 256, 512. Yeah, that's why you can buy a 64 gigabyte iPhone. You can buy a 128 gigabyte iPhone, but you can't buy a 100 gigabyte iPhone. Yeah. right? Because everything is based on the binary system, and it would be ineffective to have anything other than 2 to the power of 1, 2, 3, 4, 5, 6, 7, and so on. Yeah. So because computers internally store information in this way, that's why we have those fixed numbers. Hard disks are different. Hard disks, for example, they're just disks. We store magnetic information on them. We can do hard disks a bit bigger, a bit smaller. But solid state disks, the kind of things, solid state memory, what would be in your device, it would be basically be stored as a huge matrix of physical components that can take over one of 2 states. That's why we use the binary system here. Okay, we've got another system at our disposal as well, and that's the hexadecimal system. And in the hexadecimal system, we've got 16 different symbols. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have A, B, C, D, E, F. Yeah. So let's count up in the hexadecimal system. So the lowest number is 1. What's the next one? The lowest number is 0. What's the next one? 1. Yeah. And the next one? Yeah. And then we hit 9. What's after 9? A. Yeah. And then? Yeah. And what's after F? 1, 0. Yeah, very good. And what's after 1, 0? 1, 1. Yeah, until we hit 1F. What's after 1F? What's after 1F? 2, 0. Yeah, okay, and so on. Yeah, it goes up to FF. So why are we talking about this? Because this is what we're gonna use to store colors in HTML. Let's get my calculator out. No. Why is my keyboard not working? Yeah. Hello. Let's try again. Calculator, here we are. Can you see it? It's a bit small. Ooh, can I make it bigger? Well, this made it bigger, but the font is still tiny. Well, this is annoying. Can you, in the first row, can you read it? Okay, you might, can you read it in the last row? No, okay. So I can type in hexadecimal numbers here, so I can type in FF, for example. Yeah. So a hexadecimal FF is a decimal 255, yeah. So we, by having 2 hexadecimal digits, we have 256 possible combinations. Yeah. So on the web we use hexadecimal numbers just because it means by typing in 2 numbers we can express any value between 0 and 256 possible combinations. They could have made us type in binary numbers, but then we would have to type in 8 different digits between 0 and 1. Or they could have made us type in decimal numbers, but for some reason it was decided we use hexadecimal numbers. And that is, because it makes it easy for us to type in a value between 0 and 255. Okay, let's move on with our slideshow here. For you. On a scale of 1 to 10, how likely is it that this question is using binary? Who's getting the joke? Well, if the question is binary, what is 1, 0? I'm not joking. I once was in a supermarket, and I'm not joking. There was a person with a T-shirt on that said there are 1, 0 types of people in the world: those who understand binary and those who don't. Okay, let's move on. There's another joke waiting for you in the end. Oh, excited? Yeah. If you can't wait, I'll jump straight to the. Anybody doing Sudoku here? Do you know Sudoku? No. Hey. Do you know this one? Yeah? So binary. Here we are. Ta-da! This one, that's Sudoku. Yeah. So binary Sudoku, I think, would be quite easy to solve. Okay, let's jump back to the beginning. Here we are. Okay. Who used watercolors as a kid? I used watercolors. You use watercolors? Who used those as a kid? Me. You still do? With your daughter? Oh, good. Hope she doesn't make too much of a mess. Have you used watercolors as a kid? No? Not common? Very common in the West. And if let's do the test. Oh, I'm going to ask the ones first who has not used watercolors. I need a volunteer. Who has not used watercolors? Have you used watercolors? Have you used watercolors? No. Yeah? Okay. If you mix yellow and blue, what color do you get? Yellow and green. Green. Oh, but you know the answer anyway, so I'm happy about that. How do you know? Common knowledge. Okay, I'm happy with that then. So we don't need watercolors. I mean, in my mind, I know how to mix colors because of watercolors, but you can have the knowledge from anywhere else. So let's say we mix yellow and red. What do we get? Anyone? Yellow and red? Orange. Orange, yeah. Okay. So there are two types of mixing colors, and they work very different. When we think about mixing colors, we usually think about subtractive color mixing, and that happens in a different way than additive color mixing. Subtractive color mixing is basically we have a white sheet of paper. Our white sheet of paper reflects the light. Yeah, the light is from somewhere else. I'm deflecting the light. If I don't put any paint on at all, white gets deflected. The more paint I put on, basically, the more pigments I have that block the reflection of light. So if I mix all the colors together, I get some sort of dark color that's a bit like black. So all the colors together, if I mix blue, green and red together, I would kind of get some shade of red, black. And yeah, if I mix, for example, yellow and blue, I get green and so on. There are those very cheap inkjet printers. They don't have a separate black color. If you print on those very cheap inkjet printers, and you want to print black, it's basically mixing the other colors together. More expensive for you, because you have to pay for 3 drops of ink instead of 1 drop of ink. And it doesn't look as good, but it's kind of, you know, nearly black. But it's cheaper to make it that way. Now, in a computer, mixing colors does not work like that, because when we create web pages, they're usually displayed using some sort of screen, and if we have some sort of screen, a screen is usually not reflecting the light, but a screen is emitting the light. So on a sheet of paper, you know, no color at all is white. All the colors is black. If we work with light, it's the other way around. Yeah, if I turn the light off in this room, if I don't turn any light on at all, it's black. But if I do all the colors together, then we get white. So you see, it's exactly the opposite. If I had 3 torches here now with 3 different colors, and I would shine them on the wall, we'd get a picture similar to this. So normally, in our normal way of mixing colors, for example, you know, if we want green, we mix yellow and blue. But in this way of mixing colors, green is its own color, and if we want yellow, for example, we mix red and green. If you mix red and green with watercolors, you get a very different kind of color. So the first thing we need to think about is that on web pages, mixing colors works differently, because we use additive color mixing, because we work with light, we don't use subtractive color mixing. So the model we use is the RGB model, red, green and blue. Printers, for example, they not only are they subtractive instead of additive, they use CMYK, for example. So there are different models out there. But for the web, we use RGB, which means basically we mix all our colors that we want on the website together by using red, green and blue. So if I want black, look, here's a black spot. Now think about my question. Here's a black spot. How much red is here? Lots of or nothing? Or nothing. How much blue? How much green? Okay, I want white. How much red? All of it. How much green? All of it. How much blue? All of it. Yeah? If I go very close to the wall here, and I can actually see that the picture here is, this is not pure white. It might look like pure white from your point of view, but if you get very close, you can actually see that there is green and red and there's blue. Yeah. If you have a raindrop falling on your mobile phone screen, the raindrop could act like a magnifying glass. So sometimes you can actually see that pixels consist of red, green and blue. Have you ever noticed that on your phone? There's a raindrop on it? Yeah. More difficult now, because all the new devices have very high pixel density. But on the old devices it was very obvious. But the new devices have such a high pixel density, even with a raindrop on your screen, you probably still can't see the bits, the colors are made from. Okay. So in the beginning, with HTML, there were 16 standard colors. When we want to run any of those standard colors, we just had to use the name. I have 17 in brackets because we've got the British and the American spelling. So blue, I think, is obvious. Black is obvious. Aqua. Any idea how could aqua look like? Light blue, I would think so too. Never sure how to pronounce that. Fuchsia? Fuchsia. Fuchsia. Okay. Did I say it right? No, I didn't. It's a flower, is it? Yeah. But the problem is the flower. My mother had the flower, and it's red, and it's pink, and it's purple. Different bits of the plant have different colors. So I'm not sure what actually fuchsia or whatever. I can't pronounce it. Yeah, I'm not sure whether it's pink or purple or red or whatever it is. There's gray. Green is obvious. Lime. Any idea how lime looks like? Have a guess? How could lime look like? Lime. Lime.
Orange.
No, it's a light shade of green. There's a fruit called a lime, which is, lemons are yellow and limes are green. Yeah. Maroon, I think that's green. I'm not sure whether maroon is brown or red. Bluey red. I thought it's kind of a browny red or a reddy brown or I don't know. And navy, I guess it's a dark blue. Olive. Olive, I guess it's a bit like your top. I would call that olive. No, the color of your top. Oh, do you think so? His top is olive. Purple, I think is obvious. Red, silver, teal. Grey, yeah.
I'm not sure.
Not sure. So, and that's just 16 colors. And actually we have access to 16.8 million colors. So imagine you'd have to remember 16.8 million names when, 16 colors is already a problem, at least for me. So imagine there were 16.8 million names for colors. That's why actually, instead of describing them, we can just use a hexadecimal code for each color. Yeah. Later more colors were added. Let's click on that link. Yeah. So later more colors were added. So there's an official HTML color called Alice Blue, Antique White, Aqua, Aquamarine, Azure Beige. Beige was easy. Bisque. Yeah, I wouldn't have known what color bisque is. Blanched almond, burley wood.
Teal's actually greeny turquoise.
Let's go down to teal. Teal. Oh yeah, here. It's a bit like a darker version of the Siemens color, I guess. Salmon, sandy brown. Oh, yeah, let's go to fuchsia. Yeah, good point. That's one of those three colors that my mother's fuchsia said. Okay. So, but instead of remembering all those names, we can make up any color we want. So we use RGB, then green and blue, 3 bytes. Sorry, 3 byte hexadecimal number. So a byte is 8-bit. Yeah, so 8-bit, we talked about it before, is 256 possible combinations. With a hexadecimal number between 00 and FF, we have 256 possible combinations. So we've got 8-bit for R, for that, 8-bit for green, 8-bit for blue. So 8, 16, 24 bits. So we've got 16.8 million possible combinations. 2 to the power of 24. Or 256 to the power of 3, that's where we get 16.8. So basically that we can describe between full on that and no that at all. We've got 256 levels. We've got 256 levels of green, between no green at all and full on green, and 256 levels of blue. So here's an example. Yeah, come on. In this case, no red at all, no green at all, no blue at all. Let's go back. That's what we have here. No red, no green, no blue. What color do we get? Black, yeah. And now here, full on red, full on green, full on blue. Yeah. Full on red is in this circle, full on green is in this circle, full on blue is in this circle. So we get white. So yeah, look at yellow. What is yellow made of?
Full on green.
Full on green and full on red. Yeah. So if you want to do yellow, if you want to make the brightest yellow you can, what would be the code? Which colors you just said? Full on?
Red.
And?
Green.
Okay, so what would be the code for the brightest yellow we can make? Very good, exactly. So FFFF00 would be full on yellow. FFFFF is full on white. Yeah. So this here, for example, is somewhere between white and yellow. Yeah. Because it's not full on white, it's not full on yellow, it's somewhere between white and yellow. So it's gonna be a lighter or a darker shade of yellow. You tell me? Lighter shade of yellow. Yes, it's between yellow and white, so it's a lighter shade of yellow. We can also think about it as, if you look at the color wheel, look, yellow is the opposite of blue. Yeah? So yellow was FFFFF, which is the opposite of blue. So would be 0, 0, 0, 0, F. So we can make up any color we want out of a palette of 16.8 million by using this system. So sometimes if you just want that, in your HTML code, you can just write that. Yeah. If you just want blue, you can just write blue. You don't need to type the hexadecimal code. But the good news here is, let's say you got a logo. Let's say, can I use your cup as an example? Thank you. So this is Starbucks. Starbucks will have a shade of green. Let's say you make a website for Starbucks. You don't want the logo in one corner and the green in the rest of your page will be a slightly off green. You want exactly the same green. So you can basically go at the logo, you can use a graphics program and you can basically check what's the hexadecimal code for my logo. Your logo would be a JPEG file or a GIF file or a PNG file. We'll talk about those later. And you can basically check what's the hexadecimal code in my logo, and you can then use exactly the same shade of color on your web page. And we are nearly out of time, but here's a very simple example. Here I color the whole page in this example. So far we've only seen the body tag with nothing in it. But in this example, I spell out a background color. So I took this code, I put it on this web page. Let's have a look. When I click on that link, what we're gonna see. So I click on that link. Yeah, and here it is. Yeah, let's zoom out. Yeah. So this code created this web page. It's a light yellow background. Obviously, it depends on your screen. On my screen, it might look like lighter yellow than on the project. Okay, so that's it for now. And did Fu Yushen come in the end? Fu Yushen here? No? Okay. Okay, so see you in the workshop. I will put a new task on GitHub. It's not there yet.